I have changed the sample to some TM grids that I have put on some gold colloidal suspensions on. And the idea of this lesson is to study a little bit about the impact of using different types of voltages. What happens when you drop the voltage and so on. And also we're going to talk about this, how to make a map to guide you around that is taken by a mobile camera and so on. We can go up in voltage to 20. I want to have 20. And now it is a little bit these gold nanoparticles. I'm not sure the size of those, but they are, I guess they are rather small. So it is a little bit of high resolution work, we can say. So here we see these two TM grids, and we're running at 20 kilovolt. And the stage is not at the correct working distance, so we need to fix that first. You want to fix this, or you are the boss here now? Now we see the spot size is 30 nanometer, beam intensity is 16. We are in analysis mode. We are on working distance about 10 millimeter. So all these parameters is not really good for high resolution work. There is really small nanoparticles. So step one is to go to UH resolution, of course. So here is the UH resolution mode, and we are at 20 kV, and beam intensity is 16. Now the spot size shrunk to 4.6. So let's raise the stage a little bit, since we are going to use lower voltages over time here. Now we don't have any detector inserted, so it will be fine to go up to 5. Can focus on that little dot there, perhaps. So now we see we're on 2.9. And let's see what the smallest spot size we can get is. What beam intensity corresponds to the smallest spot size? 16 intensity gives 2.9. But we can ask the machine to tell us what beam intensity is the optimum. And then we see in this case, beam intensity 1 gives 1.7. So it can fluctuate. Last session, we was at a higher number. But 1 is a very low intensity also. So we can see how much do we have to pay if we go to 5. You see, it's still 1.7.
Okay.
So, and if I go to 7, it's still 1.7. 8. Now it starts to go up.
I see.
So you can perhaps stay on 7. So what do we have here? The whole grid here. So what have we been doing here now? We basically have 2 grids there. And we can see that one grid is a little bit brighter, another is a little bit darker, barely noticeable. And the reason for that is that I have taken 2 TM grids and put colloidal gold particles on them, on the top side, on the carbon coating. And then by intention, I flipped one upside down. And the reason for that is then the particles will be underneath the carbon coating on one of them. And as I say, how do we know which one has the coating on the top side facing us and which one had I been facing down? We can cheat a little bit by looking on the brightness. We can see that this one is a little bit brighter on the copper ring here. So that means this is the backside we're seeing.
Yeah.
But sometimes it's not easy to see, right?
No.
So then comes the idea, we can use other information to help us navigate around. And that's the reason why I had taken a picture of this sample before we loaded it in the machine with my mobile camera, and then I load it up in the machine. So there's something called in tools expositional coral here, and here we can import that image, and the image is this one. So here is my mobile camera image of the stub. And now we want to calibrate this, and so what we want to do is mark out features that we see here that we find in the SM image. So we do by putting out like 2 points. And then I can see, you see all grids, they have a number in the corner here. This is actually a number 1. You can see there it says number 1.
I see. Okay.
So that is a nice thing we can identify. So let's take the edge there. Now it became a mark there, you see? And then we click in the SM image. Where do we see that? Here. There it is. And then we take a second one, and then we can try to find some other thing to navigate. We can try to guess exactly on the midpoint between these 2 grids. Let's try that. That's about here. And then will be about here. So now we have a correlated, calibrated image. Click OK. And then we can see that image overlaid now there.
I see.
And if we did the calibration a little bit wrong, we can go in here also and click calibration and do some manual adjustment on it. But I think it's rather okay as it looks. So now we get this overlay, we can directly see from the photo. I mean, here we see that the copperish is the backside, of course. It's easily seen in the mobile camera, but in the SM it was not so easy. But now we directly know that the bottom one here is the one that's facing backwards.
Yeah.
So this is a nice thing, and we can also remove this and see just the SM image. And then we can use this as a navigation map. You see there is a box here. That is the actual view field we have in the SM. So if I, for example, do the rotation here, you can notice this box moves, it rotates. So then it directly can navigate. If we zoom in, you see the box becomes smaller.
Yeah.
And then I can click also. Let's say I want it, that's the hole where I put the tweezer in, right?
Yeah.
If I double click on that, it moves the SM to that hole now.
I see. Okay.
So now I can see, here is a hole that I see in the photo, and then I can investigate. It's very handy when you have like features you can't see in the SM, but they are clearly seen in optical micro. I took this with my mobile camera, but I mean you can do it all with the optical microscope. Any kind of digital images work. So this is a very handy thing to have that kind of map tool. So now we are looking on the back side, the grid that's flipped back, and this is the one that is facing in the right direction. So let's go back to UH resolution now. Here you see lines, right? Zoom in even more. You see the lines. Now the lines goes in the other direction. So we want to find the true focus, which is there. Stigmatism, you correct on the board, make the image sharp. Try up and down. Good. Try left and right again.
Yeah.
All right. So now we can zoom in even more. You see, line still comes, right? can also check the column centering. Now you should see how it looks like. You see, you can change the wobbler intensity. If you pull that down a little bit, it becomes a little bit easier. You see, no, wait.
Sorry.
You see, it's, I think it was pretty good as it already was, right?
Okay. Yeah.
So the column centering is fine, but the stigmatism we can improve, right? See here, it becomes a little bit lineish. Very little there. Try to see if you can adjust a little bit. Look on these particles you see here. Try to make them as sharp as possible.
Mm-hmm.
See, now they are pretty sharp. Try a little bit up and down now. A little bit down. There you go. There you go. Now a little bit left and right. Now go back a little bit. About there, right?
Mm-hmm.
And now you see, you can zoom in a little bit more. This is the max on the machine, 1 million magnification now. You see that we have a little bit drift since these particles are on that thin carbon film, and that moves a little bit and so on. And, but we can try to scan this image. Let's try to make an image now. Small. We take the smallest pixel size now, and we want to scan it without any integration here. Go out the contrast. And we scan the image. So let's look on this. What is the size of it? Take the measurement panel. Oh. So the particle is 10 nanometer. It's a pretty damn small particle. And the spot size we're using now is 1.7. And this machine has a line resolution 1 nanometer. And that is if we're using at 1 kV. Now we're at 20 kV. So the higher the voltage, the easier it is also to maintain a high resolution. But the thing with the high voltage is that we also shoot straight through everything. So what we can do now is let's go and look on the particles that is you can see that, I mean, these bars, that's the copper mesh, right?
Yeah.
And then the carbon film covers the holes, but some places it has broken. Here you see it's broken. Here's a crack also, and here's a big hole. So let's go over now to this other grid. We can use the map perhaps. Here we want to go to this one. So now we are on the copper grid that's flipped back side up. You see the bars is brighter because the carbon film is underneath now. So now we want to see if we can find particles around here also. Okay, but let's start from here. So we took this image on the grid that was facing upwards. So here we have the gold nanoparticles on top of the carbon film. And this was on 20 kV. And then we moved over to the grid that is flipped upside down. So that is the thing that we're monitoring right now. So here, this is on a lower magnification also. It's like 10 times lower magnification. And we can scan here perhaps. See the image. So now we are seeing the particles that it's on the back side of the carbon film. And the carbon film is about 200 nanometer. And the particles were about 10 nanometer in diameter, right?
Yeah.
So what I want to show here is what happens when we drop the voltage. So now we have already dropped the voltage to 5 kilovolt. We still see the particles, but they are a little bit more blurred because they're on the back side. So resolution-wise, it's not advisable to look through a window when you can go to the other side of the room, so to say. But let's drop the voltage further now. You can go to 3, something like that. It's the same U field, I think, 100 times magnitude U field. Still see particles. They become more blurred, of course. And then we go to 2 kilovolt. Demonstrate that low voltage operation gives you more and more surface features, and we cannot see things that's inside materials as we see in high voltage. So when we started running at 20 kilovolt, and then in this part the particles was on the top side. So this was the most, what shall I say, favorable imaging position. So let's go back now to this top side. And what you can do on this machine is that one can right-click here and choose Restore Image Condition. Then it will go change everything back and go to the same position. And it says this is a risk, it can crash. So I mean, of course, you cannot load the image that you took yesterday because you must have the same sample on the same position. So you can only do this during the same session, so to say. But it is a nice tool when you want to revert back to a previous place.
So it brings it to the exact same place?
Yes. Now this was at the highest magnification, so it might be a little bit offset since the stage will be moving.
Yeah.
But we will see where we end up. Trying to figure out if we can see that old place. And since there's a mechanical motion on the stage, there is like 1 micrometer error in the motion of the stage. So since this is like super high resolution, that obstacle, I'm wondering if we can see that. But we are in the same area at least. But let's see if we can improve this resolution on these particles. How does it look like if we run 5 kilovolt here, or even lower? Let's try 3 kilovolts. And then we raise the stage also. Since I said earlier, we want to have a working distance that is not more in millimeter than the voltage we're running, right? So now we have to the left, we have 20 kilovolt. Yeah. And to the right, we have the same magnification, everything, but it's 5 kilovolt on this image. And we see the spot size has gone up since we have gone down in voltage. That is a problem, right? We see that they are not as transparent as in the left image. So we don't shoot straight through the particles at 5 kilovolts. So the contrast is better, but the resolution is worse. So this is the case when you would like to use like this beam deceleration mode, beam deceleration. But actually what it do is that if we look on the stage here, if we go to beam deceleration mode, it will put 5 kilovolt on the stage. negative 5 kilovolt. So that means it will repel the electrons. So then we can, if we have 3 kilovolts now, then we shoot from 3 kilovolt and then we go to 0 potential. But if we raise the stage to 5 kilovolt, then we can have a higher voltage on the gun, and then the difference, we can have 8 kilovolt on the gun, then the difference will still be 3. But for most of the path in the column, the electron can use the high voltage. So the resolution is improved by doing that. We shall remove the EDS detector also before we change that. You see everything change in the picture when we do that. Since the EDS detector is also metal, so we need to. So let's try that. In Deceleration Mode, it says no detectors and stuff inside. So there is an issue with this, and that is that you can create a spark between the stage and the pool piece, and the machine will protect itself against it, but it makes it impossible to run the sample if you create a spark. So it's the sample. If the sample have like very sharp edges and things like that, then creating sparks is more easier. So now you see this became red. And you say, we even got a spark, you know. So arc says.
What's the problem?
I think I know it can. The sample doesn't like. You cannot have sharp objects on the sample, and I think when we made this hole here, there is a copper pin pointing out that creates that sparking for us.